Okay, can I have everyone's attention, please? Let's go ahead and start. I wanted to make one announcement, and that is that you know that there's a midterm coming up next Wednesday. A week from today, we have the first midterm exam. And in preparation for that midterm exam, the Chem Department tutors will be holding a review on Friday from 5 to 7, all right? And that information is on the class website. During the first hour of that review, I will be there to answer any questions. So this is a good opportunity. If you have any questions, please come prepared. So you should have studied the materials. So when you have a review, it is a review after you've studied the material rather than, sort of coaching you. All right? So please come prepared. It's on Friday from 5 to 7 p.m. and the information is on the class website. Okay? Now, we're going to pick up where we stopped last time. And if you guys remember, last time we talked about acid-base properties of salts. And we said salts are ionic compounds. Another word for salt is an ionic compound. And we said if you take salts, they can be either soluble in water or insoluble in water. The majority of them are soluble, all right? And if you take the soluble salts, we said the moment you put a soluble salt in water, it dissociates completely. So if you take sodium chloride and you put sodium chloride in water, the instant you mix it up with water, it dissociates completely. So I want to show you a molecular level picture of what happens. Okay, so we have sodium chloride, and let me start that again. I have the wrong one, so I'm going to have to go find the right one for you. They have categorized it incorrectly. So just give me a moment to pull it up. There we are. That's the right one. Okay, so I wanted you to take a look at this picture. And what you see at the beginning is a sodium chloride as a crystal. So you can see that it's an ionic structure. The yellow one, the green ones are the chloride anions. The gray ones are the sodium cations. Remember, cations are always smaller than anions. In the ionic solid, they're packed together as a lattice, so you can see the lattice structure. And then what happens is when you pour water on top of it, you can see the whole structure disintegrating as water molecules wrap themselves around the cation and anion. So you can see in this corner here, you can see the ionic solid. So here are the cations and anions. The green ones are the chloride anions. The gray ones are the sodium cations. And so when you begin with, this is what the ionic solid looks like, all right? And we're at room temperature, so you can see that they're vibrating, but their location is the same. So they vibrate about a fixed location. Now when you pour water over it, you can see now that the water molecules are attracted to the chloride anions and the sodium cations, and so as a result of that, the whole structure starts disintegrating and falling apart. So you can see that the cations and anions are removed from the lattice structure and the whole structure disintegrates. Now once you form the sodium chloride solution, this is what it looks like. So here, now after the sodium chloride has dissolved completely, you can see here's a chloride anion, all right, surrounded by water molecules. And then you can see the sodium ion coming up. There's the sodium ion. Occasionally they'll come and bump against each other, and then they'll go away. All right? So what's happened is the water molecules are in such large excess that in the end, every cation and anion will be surrounded by water molecules, and they're separated by great distances because there's so much solvent molecules compared to the sodium chloride ions. Okay? So if you wanted to write down in the form of an equation what we just saw, so what we looked at was when you take sodium chloride, this is a salt, and in water we said it dissociates completely to give you Na plus Cl minus aqueous. In reality, if you take Na plus, and if you want to represent that cation as a sphere, remember they're in the same period, so if you compare the size of the cation to the anion, we know that cations tend to be smaller. So the smaller one would be the sodium cation, and anions tend to be larger. And so if you take the cation is positively charged, and we know water molecules are polar. So you have delta minus, delta plus like that. And so it turns out the reason they dissolve is because the attraction to the water molecules is greater than their attraction for their counterions. So in the sodium chloride solid, what holds it together is electrostatic attractions. But the moment you put it in water, the attraction for the cation and anions to water is greater than the attraction for each other, and therefore it dissolves. And so when this structure is represented as Na plus aqueous. So within parentheses, when we say it's aqueous, it means that it's surrounded by water molecules. Likewise, you have Cl minus. Now Cl minus is bigger size-wise, and it's negatively charged. So now what happens is that the delta plus end of the water molecule will be attracted to the chloride anion. And so these water molecules will wrap themselves around the anion, and this is the reason why soluble salts dissolve. All right? Now we said salts can be insoluble as well. When you look at insoluble salts, it turns out the attraction for each other is far greater than the attraction for water, and therefore insoluble salts don't dissolve in water, they just sink to the bottom, and we call those precipitates. All right? Right now we're interested in looking at soluble salts. And we said that soluble salts like sodium chloride can act as an acid, base, or a neutral substance in water. And for you to figure out whether it's going to be an acid, base, or a neutral substance, what you have to look at is the cation and anion that make up that substance or salt. And we have rules for that. So if you take the anion, we know that if the anion part of it is a conjugate base of a strong acid, we said it's going to be neutral. If the anion is the conjugate base of a weak acid, it will be basic in water. All right? Those are the only two choices you have. If you take the cation part of it, we said if the cation turns out to be a group 1 metal or a group 2 metal, it's going to be neutral. So if it's like sodium, potassium, and so on, it's going to be neutral. If the cation is the conjugate acid of a weak base, then it will act as an acid. All right? And so if you look at the table that that list of acids and bases that I gave you that is on the class website, you can see that anything that's in red, these conjugate bases, these in red, these are the conjugate bases. So these conjugate bases that are highlighted in red are the conjugate bases of strong acids. So if your anion of your salt is any one of those, you know it's going to be neutral in water. All right? If your anion happens to be any one of these conjugate bases that have negative charges, okay, so look for the ones that have negative charges. If you look at this, urea is neutral. So if it's neutral, it can't act as a cation or anion. All right? So leaving that out, if you look at everything else that's negatively charged, all of these will act as a base in water. All right, if they're counterion, if the cation is sodium, potassium, or group 1 metal, all right, then these anions, the salts that these anions form, will be basic in water. Okay? Now, if you're talking about conjugate acids of weak bases, if you look at these, any one of those that are positively charged here, can you see this one is positively charged? That means it can act as a cation, and therefore in water it will be acidic. So here's one example, and as you go down, anything that has a positive charge here, this one is the pyridinium ion, and this has a positive charge. Therefore, if you place it in water, this will be a weak acid, all right? Because this is the conjugate acid, its base would be this, and therefore this can act as a cation. Likewise, NH4 plus is the conjugate acid of the weak base NH3, therefore this can act as a cation. All right, so as long as you have this table in front of you, you can identify the ones that will act as conjugate acids in a salt. Because for a salt, you have to have a cation and an anion. The acid form, if it has a positive charge, it can act as a cation. And then on the basic side, if it has a negative charge, it can act as a weak base when it's a salt. Okay? So now all we have to do is work some examples of trying to figure out the pH of salts. Okay, so the next part is just calculating the amounts of hydronium ion or hydroxide ion. Okay? So here's a question where, once again, remember one of the kind of themes that we've been developing is that you should be able to calculate the pH of any kind of solution, whether you have a weak acid, strong acid, whether you have a weak base, strong base, whether you have a polyprotic acid, regardless, any one of these examples that we've looked at, you should be able to calculate what the pH is, all right? So in this example, we are asked to calculate the pH of a 0.1 molar ammonium chloride. So your starting point is you look at the substance that's given to you. You ask yourself, overall, is that substance a weak acid, strong acid, weak base, strong base, polyprotic, or is it a salt? All right, because those are all the examples that we've looked at. So when you look at that compound, how would you categorize that? It's a salt, okay? So that means if it's a salt, you know that obviously the ones that they're giving you should be a soluble salt, because if it's not soluble, you can't calculate the pH, okay? So this is a soluble salt, and you know that if it's a soluble salt, the instant you put it in water, what will happen? It's going to dissociate. So we know that if I take ammonium chloride, I know that the instant this dissolves in water, just like that picture that I showed you, it's going to dissociate completely in water. All right? And we know that we started with 0.1 molar, therefore the concentrations, because when they dissociate, it's a 1-to-1 stoichiometry. Every unit of this will give you 1 unit of NH4 plus and 1 unit of chloride minus. So if you start with 0.1 molar of this, you know that when it dissociates, you're going to get 0.1 molar of each of those. Now you look at this, and let's look at the basic form. You know that this is the conjugate base of a strong acid. All right? Would the conjugate base of a strong acid be acidic, basic, or neutral? Neutral. So we know that this component is not going to affect the pH. Now let's look at the other part, which is the cation. Look at this. This is the conjugate acid of a weak base. Is the conjugate acid of a weak base acidic, basic, or neutral? Acidic. All right? So that means that if we want to calculate the pH, we know the component that's going to affect the pH would be NH4 plus, right? So if it's NH4 that we're going to focus on, and we know that if we want to write the equilibrium, this is the acid form, and therefore it's going to act as an acid in water, therefore it's going to be a proton donor. So if I take NH4 plus and place it in water, we know that this is the proton donor, this will be the proton acceptor, therefore we'll have H3O plus aqueous plus NH3 aqueous. And this form of the equation gives us what? Ka. All right? But what do they give us? they give us the Kb for NH3. Do you see that? They give us Kb, therefore we have to convert it to figure out what Ka is. And we know that Ka is what? Kw divided by Kb. And therefore this would be 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which gives me 5.6 times 10 to the negative 10. All right, so that's an extremely weak acid. All right, so the next step is now for us to figure out what the hydronium ion concentration is in this equilibrium, and that would give us pH. Okay, so how do we set about doing that? We start by saying the initial concentrations, all right, in molarity, and we know that we start with 0.01 molar of ammonium, so this would be 0.01 molar. We're not concerned about the concentration of water. To begin with, we have none of the products being formed, so that would be 0. Then the change would be, it's going to have to proceed in the forward direction because there are no products. We need to form some products to establish an equilibrium, so we know it's going to proceed in the forward direction. Therefore, some of the reactant is going to be consumed, and some product is going to be formed, and the stoichiometry is 1 to 1 to 1. Therefore, at equilibrium, I would have 0.01 minus x, x, x. So you can see that there's a general pattern to solving all these problems. Almost every single problem that we've handled, whether it's a weak acid, weak acid, weak base, polyprotic acid, any one of these examples is the same approach. All right? So now what I need to do is I know Ka equals 5.6 times 10 to the negative 10, which equals the hydronium ion concentration times the concentration of ammonia divided by the ammonium cation, all right, which gives me x squared over 0.10 minus x. Now, look at our Ka value. Our Ka value is 10 to the negative 10. That's a really, really small Ka value. So can I make an approximation here? Yes. So if Ka is that small, I know that x is going to be really small because it's going to only react to a very small extent. All right? So that means that I can make the approximation. And my approximation is going to be that 0.01 minus x is going to approximate to 0.01. In other words, that x is going to be so small that I can neglect it. Okay? So therefore, I can go back and I can say 5.6 times 10 to the negative 10 equals x squared over 0.1. And so if you solve for x, x comes out to be 7.5 times 10 to the negative 6 molar. All right? Now what do I do next? Yes, don't go ahead and quickly calculate the pH. Not yet. You have to make sure whether your assumption is correct. Remember that that is an assumption that we made, and we have to check to see whether that assumption is appropriate. Okay? So if I check the validity of my approximation was what? That x is really small compared to 0.1, so small I can neglect it. So that means 7.5 times 10 to the negative 6 molar divided by 0.1 molar times 100, and that comes out to be 7.5 times 10 to the negative 3%. So that's 0.007. That's well below our 5% threshold. Okay? So we do know that this approximation is pretty good. And so now I can say my hydronium ion concentration equals x, which is 7.5 times 10 to the negative 6 molar. Therefore, if I take the pH of that, that comes out to be 5.13. So you take the negative log of that, and my pH comes out to be 5.13. Now ask yourself, remember our presumption at the beginning was that this is the conjugate acid of a weak base, therefore it has to be acidic. All right? So now we've calculated the pH comes out to be around 5. When the solution has a pH of 5, is it acidic or basic? acidic. All right, so we know that it's in line with our prediction. Okay? So any questions up to this point? So we've looked at salts. Please, when you're studying at home and during discussion, I have given you lots of examples of problems of this type. So please make sure, you remember last time we went through, if you're given salts and weak acids, strong acids, whether you have the ability to rank them according to relative acidic strength or basic strength. In other words, can you rank them starting from the strongest acid to the weakest base, or can you rank them starting from the strongest base to on the other side, the strongest acid, okay? And when you deal with salts, you got to separate them out, look at cation and anions. If you're just dealing with acids alone, you just look at whether it's a strong acid or a weak acid. If you're looking at bases alone, you look at to see whether it's a strong base or a weak base, all right? And you should be able to rank this. And this week's discussion worksheet has some examples, and so during discussion, you'll have an ample opportunity to practice that, okay? So now, I wanted to kind of ask you, I'm going to quiz you on something, all right? So remember, so let's say we have a strong acid, which is HCl, all right? And the initial concentration of HCl is 1 times 10 to the negative 2 molar. So since this is a strong acid, what is the pH of the solution? pH is 2, all right? Because you don't need a calculator, all right? You know that the pH is 2, all right? So if the initial concentration of a strong acid like HCl is 10 to the negative 2, you know that the pH is 2, all right? Now, if my initial concentration of acetic acid is 1 times 10 to the negative 9 molar, what would the pH of the solution come out to be? 9? Now tell me, if pH is 9, is that solution acidic, basic, or neutral? Basic. So can you add a strong acid and end up with a solution that is basic? No. So there's a problem here. And the reason is that you're in water, all right? Up to this point, every example that we looked at, our concentrations of acids was so large that we ignored water. So when you have the top one where it's 10 to the negative 2, we know that the hydronium ion that comes from HCl is 10 to the negative 2, but in the background you have water. And what is the concentration of hydronium ion in pure water? 10 to the negative 7. So if you compare 10 to the negative 2 that comes from the strong acid and the 10 to the negative 7 that's there in pure water, you can see that the 10 to the negative 7 is so small you can ignore it. All right? And so what we focus on is just the 10 to the negative 2, because the difference between 10 to the negative 2 and the 10 to the negative 7 is an enormous difference, so large that you can ignore it. All right? Now when we go to a strong acid that has something like 10 to the negative 9, now what happens is HCl produces 10 to the negative 9 hydronium ion, but pure water produces what? 10 to the negative 7. Do you see that? And so now, that's a bigger number than this. So if you take a solution like this, then what do you think the pH of that solution should come out to be? 7. All right, it's going to be a neutral. All right, because now the 10 to the negative 7 is 100 times greater than 10 to the negative 9. All right, and therefore this solution would have a pH of 7. All right, now if the difference between 10 to the negative 7 and the acid that you add is large, then you take whichever is large. If they're in the approximately similar range, and that is between something like 10-fold within. So if you have an acid that's 10 to the negative 7, pure water that's 10 to the negative 7, both are 10 to the negative 7, pH is going to be approximately 7. If you have the acid that you add is 10 to the negative 6, and water is 10 to the negative 7, so there's a 10-fold difference, then the problem gets to be more complicated, because now they're in the same approximate ballpark, and now what you have is you have two competing equilibria, all right? And so that means now if you want to figure out what the pH of that solution is, it's going to be a little bit more complex, All right? And at this level of class, we're not going to look at calculations where you have two competing equilibria like that. But if you take a more advanced class like analytical chemistry, you will look at two competing equations, two competing equilibria, and figure out what the ultimate pH of that solution is. All right? So whenever you look at it, see a question of this type, make sure that you go back and ask yourself, is my pH consistent with whether that solution is acidic or basic? All right? And so this is examples where your acid concentration is so dilute that now water has to play an important role. Okay? Up to this point, every example that we took, the concentrations where acids were of the order of 1 molar, 0.1 molar, or 0.01 molar. So if you're dealing at that concentration range, you can ignore the contribution that comes from hydronium ion. All right? Okay, so we have kind of completed looking at chapter 11 of your textbook, where we looked at acid-base chemistries. Okay? Today we're going to move on to another topic that's related to aqueous equilibria, and we're going to start looking at application of Le Chatelier's principle. Okay, so application of Le Chatelier's principle to acid-base equilibria. And we call this the common ion effect. All right? So if you recall, when we looked at equilibria last quarter, we talked about Le Chatelier's principle. And we said we use Le Chatelier's principle to figure out how a system responds if you disturb a system that's at equilibrium. So if you take a system that's at equilibrium and disturb it in some way, we know that ultimately that system is going to go back to equilibrium. And so we can make predictions about how it will respond in order to go back to equilibrium. Okay? So we're looking at acid-base equilibria. And so let's take an example. So let's say we have a weak acid. So we have HF in water. All right, so this is a weak acid. So therefore HF will be the proton donor. Water will be the proton acceptor. So can you tell me what the products of this equilibrium should be? H3O plus and F minus. Okay, so this is the equilibrium. So let's say we have a system, a weak acid, that has established this equilibrium. And we know it's a weak acid because Ka equals 7.2 times 10 to the negative 4. Okay, so this acts as a weak acid. And so let's say this system has established equilibrium. All right? After equilibrium is established, let's say we add the salt, sodium fluoride. So all of you can recognize that what we're adding is a salt because it's got an anion and a cation. And if this is a soluble salt, what will happen? The instant I add that salt to that solution, that equilibrium, what is going to happen? It's going to dissociate. All right? So this will dissociate to give me Na plus aqueous plus F minus aqueous. So can everybody see that when I add this salt to the system that's at equilibrium, I'm actually increasing the fluoride ion concentration. And so by increasing the fluoride ion concentration, I'm disturbing that equilibrium, or I'm stressing that equilibrium. And we know, according to Le Chatelier's principle, if you disturb an equilibrium, it will react in the direction in which it'll counteract that stress. So what was the stress or disturbance? I added extra fluoride minus. So what is my stress? Too much fluoride. So the system will respond to counteract that stress. So that means it has to reduce the amount of fluoride. Okay? So if you take the equilibrium, there are only two directions in which it can react. It can go in the forward direction or it can go in the reverse direction. So which direction does it have to proceed to overcome that stress? It's got to reduce the fluoride ion concentration. it's got to go in the reverse, because if it goes in the forward, it's going to produce even more fluoride ion. Okay? So the system will respond by proceeding in the reverse direction until it goes back to equilibrium. All right? So we say that the system will respond by reacting in the reverse direction until it goes back to equilibrium. All right? And so this shift in equilibrium position that occurs because of the addition of an ion already involved in the equilibrium reaction is called the common ion effect. Okay, so we call this the common ion effect. So we said the shift in equilibrium position that occurs because of the addition of an ion already involved in the equilibrium is called the common ion effect. So if you're ever asked to explain what you mean by the common ion effect, it describes how the system will respond if you take a system that's at equilibrium and add a common ion to it that's involved in that equilibrium. Okay? So let's take another example. So this is an example of a weak acid. So let's take an example of a base. A weak base is ammonia. So if I take NH3 aqueous in water, by now you should know that NH3 is a base. So if I put NH3 in water, can you tell me what are the products you're going to see? Now NH3 is the base, so it's got to be the proton acceptor. And water is going to be the acid, therefore water is the proton donor. So can you tell me what the products of that reaction is going to be? NH4 plus and OH minus. Okay, great. So this would be NH4 plus aqueous and OH minus. Okay, and because we're writing this in the form of a base, we're looking at Kb, and Kb equals 1.8 times 10 to the negative 5. So once again, we know that this is a weak base. So let's say we start with this and we've established an equilibrium. Now, if I add a common ion, so let's say now into this I add a salt, and the salt that I'm going to add is ammonium chloride. So now I end up with NH4 plus aqueous plus Cl minus aqueous. So we know that when you put a salt, it dissociates completely to produce cations and anions. And once again, you can see that because I'm adding a common ion, NH4 plus, to a system that's already established equilibrium, I'm going to disturb that equilibrium. And what is my stress? Too much NH4 plus. And if the NH4 plus has gone up, that means the system is going to respond by proceeding in the reverse direction. So the reaction will shift towards reactants. And the net result is, so if you look at this, the net result is that hydroxide ion concentration decreases, and therefore, if hydroxide ion concentration decreases, what will happen to the pH of that solution? pH decreases. Okay? Now, in the previous example, The effect is, the net result is, so if we go back to the previous example that we looked at, in the previous example, if the reaction proceeds this way, all right, what happens to hydronium ion concentration? Because the equilibrium shifts towards reactants, you can see that the hydronium ion concentration goes down. All right? So in this example, the net result is that hydronium ion concentration decreases. And if hydronium ion decreases, we know pH increases. All right? So in each instance, not only do you have the equilibrium being disturbed and you have this common ion effect, but this common ion effect actually will affect the pH of that solution, because in the first example, when the reaction proceeds in the reverse direction, you know that the hydronium ion concentration is going to go down. If the hydronium ion concentration goes down, we know that the pH is going to go up. In the second example, we're looking at hydroxide, and so in this case, the net result is that it's proceeding this way, so hydroxide ion concentration decreases, and therefore the pH would decrease. All right? So not only does this common ion effect disturb that equilibrium, but it also will affect the hydronium ion or hydroxide ion concentration. So now we want to calculate that. We want to calculate and figure out how big is this effect. All right? So we're going to try to calculate what happens if you add a common ion and what happens to the pH of a solution. Okay? So to do that, remember all of these problems on the class website, so you don't need to copy it. So here's an example of a problem involving the common ion effect. So the question is, calculate the pH and the percent dissociation of HF in a solution containing 1 molar and 0.1 molar sodium fluoride. So you have HF containing 1 molar of HF, and you're adding 1 molar concentration of sodium fluoride. Okay? So we're adding sodium fluoride, so all of you recognize that because we're adding sodium fluoride, we know sodium fluoride dissociates to give you the cation and anion. And if we started with 1 molar of sodium fluoride, we know that we end up with 1 molar of sodium cations and fluoride anions. All right? So the equilibrium that we're looking at is how this common ion affects the equilibrium that we're interested in looking at, which is HF in water. This is a weak acid, so it's going to produce hydronium ion plus F minus. And we are told that Ka is 7.2 times 10 to the negative 4. All right? And this is the fluoride ion that's there. So if we wanted to look at initial concentrations in molarity, we know that we have 1 molar of HF to begin with. We are not concerned with the concentration of water. The acid hasn't reacted yet, so we're going to have 0 hydronium ion, but our fluoride ion concentration is different because we've added fluoride ions from this. So can you see that the source to begin with, there's fluoride ion concentration, and therefore that would be 1. So this is the only difference between the previous problems where we just look at HF in water and we figured out what the pH is. Now what we're looking at is not only do we have HF to begin with, but we're adding a salt that has F minus. So before anything happens, before equilibrium is established, we have 1 molar of the weak acid and we have 1 molar of the F minus ion. All right? So now solving this problem is going to take the same approach that we've done before. So what we say is now we're going to look at the change. Since we have no hydronium ion formed yet, we know that the reaction has to proceed in the forward direction. All right? Therefore, this is going to be negative x. This would be plus x. This would be plus x. Therefore, at equilibrium, I would have 1 minus x. X, this would be 1 plus x. So can everybody see the only difference here is now we have F minus to begin with, and that concentration of, if the reaction is proceeding the forward direction, then the concentration of F minus is going to increase. All right? And so now we can solve this like any other equilibrium problem. We can say Ka equals 7.2 times 10 to the negative 4 equals the hydronium ion concentration times the fluoride ion concentration divided by HF. And that gives me 1 plus x times x divided by 1 minus x. Now once again, if you look at Ka, it's 10 to the negative 4, so it's a small number, so it's safe to make an approximation. So now I can say my approximation is 1 plus x will approximate to 1, and 1 minus x will approximate to 1 as well. We're saying x is so small compared to 1 that we can actually neglect it. So now I can go back to my equation. I can say 7.2 times 10 to the negative 4 equals 1 times x divided by 1. And therefore, x is 7.2 times 10 to the negative 4 molar. I want to check my validity. Is my approximation valid? And I said x is really small compared to 1. And you can see that comes out to 7.2 times 10 to the negative 2% or 0.072%. All right? And therefore, we know that our approximation is pretty good. It's well below our 5% threshold. Okay? So now the question was, calculate the pH and percent dissociation. So now if I calculate the pH, I need the hydronium ion concentration. And we've calculated that the hydronium ion concentration is x, which gives me 7.2 times 10 to the negative 4 molar. Therefore, the pH would be the negative log of that. And if you work out the pH comes out to be 3.14. All right? And then percent dissociation would be 7.2 times 10 to the negative 4, that's x, divided by the initial concentration times 100, which is 7.2 times 10 to the negative 2%, or, as I said before, 0.072%. All right, so we calculated the pH of the solution if you have a common ion involved in that. Okay? Now, what if you want to compare this to if you didn't have the common ion in there? How would you calculate that? So let's say compare to, so let's compare this to, the absence of NaF. So let's compare this to the absence of sodium fluoride. So if I just had the weak acid, then this would be the kind of problems that we worked before. Remember, this is sort of the classic problem where what is the pH of a weak acid? You're given 1 molar of a weak acid, calculate what the pH is. You should be able to do this kind of in your sleep, huh? So what do? Write the equation. That gives me H3O plus aqueous plus F minus aqueous, and I know Ka is 7.2 times 10 to the negative 4. So now I don't have any common ion in there, so my initial concentration would be just the 1 molar of HF, not concerned about water. Since I don't have any added salt, my fluoride ion concentration to begin would be 0. Therefore, the change would be minus x plus x plus x. Therefore, at equilibrium, I would have 1 minus x, x, x. All right? So if I were to calculate the value of x, we can say Ka equals 7.2 times 10 to the negative 4, which is the hydronium ion concentration times the fluoride ion concentration divided by the concentration of HF, which gives me x squared over 1 minus x. Once again, I can safely make that approximation, so I can say my approximation in this problem would be 1 minus x will approximate to 1. So I can go back, and I can say 7.2 times 10 to the negative 4 equals x squared over 1. And therefore, if you work that out, it comes out to be 2.7. So x equals 2.7 times 10 to the negative 2 molar. All right? And if you check validity, you can see that it's 2.7 times 10 to the negative 2 divided by 1 molar times 100, which gives me 2.17%. So once again, we're okay. That number is really small. We can ignore it. And therefore, now I can say my hydronium ion concentration would be 2.7 times 10 to the negative 2 molar. If that were the case, pH would come out to be 1.57. All right? And if I want to calculate what the percent dissociation is, it's the amount that dissociated, which is 2.7 times 10 to the negative 2 molar, divided by 1 molar times 100, which is 2.7%. So I want you now to compare this with the previous problem. So in this case, if I had no salt in there, my pH would be 1.57. If I had a salt, what does the pH become? 3.14. So you can see that that illustrates that added salt will shift the equilibrium in the reverse direction. Therefore, the hydronium ion concentration goes down. So you can see that the hydronium ion concentration to begin with, without any salt, will be 2.7 times 10 to the negative 2. With the salt, will be 7.2 times 10 to the negative 4. All right? So you can see that this has, without the salt, you have a higher hydronium ion concentration. With the salt, you have a lower. If you take the pH will be lower. It's 1.57. You can see adding a salt raises the pH to 3.14. If you look at the percent dissociation, without the salt, it's 2.7% dissociates. If you add the salt, it goes to 0.072%. So adding a salt, that is what is called the common ion effect. It affects not only the pH of the solution, because we said if you disturb an equilibrium by adding a common ion, it's going to shift in the direction in which it counteracts that stress. And so the net result is what you see here. Okay? So we're going to stop there for today, and next class we'll start looking at buffers. All right?